Hi, I'm David Alvarez, and I'm presenting the paper Advanced Synchronization Techniques for Task-Based Runtime Systems. I will start with an introduction to task-based runtimes and programming models and some motivation for the content of the paper. Then we will look at the novelties presented in both data dependencies and task scheduling, and finally present the evaluation and conclusions. Current trends are pointing to systems that have each time more cores per socket, and we call them many core systems, which often have non-uniform memory access patterns or are heterogeneous architectures. These systems can achieve great performance figures, but applications must scale accordingly. To program these applications, one of the first programming models for multiprocessing was Openmp. It initially featured a fork join execution model, which is better suited for very regular parallelism, but does not work well with irregular, dynamic, or nested parallelism. To overcome this limitation, task-based parallelism was included for the irregular use case. It has some more benefits, for example, the natural ability to cope with load imbalance. With the introduction of data dependencies, we move towards a data flow execution model on which there is no need for global synchronization on most cases. However, these tasks and dependencies add runtime overhead. The anatomy of a task-based runtime system normally consists of three components: the dependency system, which manages the dependencies between tasks and provides ordering guarantees to their execution; the scheduler, which manages tasks when they are ready to be executed and assigns them to idle cores; and finally, the memory allocation, which provides dynamic memory to place the tasks and dependencies on. These components are coupled and can be accessed by multiple threads at once, and thus require synchronization, which can cause contention and add even more overhead. When working with tasks, application developers must balance task granularity. Scaling out an application with a fixed problem size requires creating more smaller tasks in order to feed all available resources. Thus, scaling out granularity is naturally decreased. At some point, tasks can become so small that the application is bound only by the overhead of the runtime, and this limits its scalability. The normal granularity versus performance behavior is shown on this plot at the bottom of the slide, which shows that we have an ideal region where granularity has a good balance between feeding all the cores, so there's enough work, and not being too small to be overhead bound. When tasks are too big, there are not enough tasks to feed all available cores, and we lose performance because we have less parallelism. On the other hand, when tasks are too small, they are overhead bound, and this is what we will study on this paper. To visualize how the three components of the runtime interact with each other, we can look at this example diagram. A task currently running on a CPU will create other tasks allocated by the memory allocator, of course, and then their dependencies will get stored and added to the task graph inside the dependency system. When the dependencies determine that this task is ready to be executed, it enters the scheduler and is placed on the ready queue. The scheduler will manage the idle cores and assign tasks to those free computing resources as it sees fit. We present in this paper three main contributions. First is a novel weight-free data structure for dependency management. Second is a scalable task scheduler that uses delegation instead of work stealing. And then we analyze in detail the performance of a task-based runtime thanks to a lightweight instrumentation framework that we built. We evaluate each contribution separately and then combine them to compare to other state-of-the-art runtimes. The contributions we explain have been applied to the Nano 6 runtime, which implements the OMPSS2 programming model. The OMPSS and OMPSS2 programming models were both created by the BSC to act as OpenMP forerunners. and feature a complex data flow execution model. However, all of the concepts that we present could be simplified to apply to Openmp runtimes. In OMPSS2, we express dependencies by annotating the data that each task accesses on a pragma, very similarly to how Openmp dependencies work. Dependency management is executed when a task is created or finished, and multiple threads can be creating and finishing tasks at the same time. So we need synchronization, and it can become a contention bottleneck. As shown in this diagram here at the bottom, there are two possible relations of dependency between tasks in OMPSS2. When two tasks on the same nesting level, so this task and this task, for example, declare an access to the same memory location, we say that the second task is a successor of the first task. If this happens across nesting levels, where both tasks declare dependency to the same variable, we say that the first task is a parent task and it has a child task with a dependency. When we declare a task with n dependencies, we create inside of the task structure a data access array, which we store all of the declared dependencies. For example, here we create a dependency to A and B, and thus in the task, we have an array that contains A and B. Its data access has the following fields, has the type of the access, the memory location it refers to, and the successor and child pointers. Also, its data access has an instance of an atomic state machine. This machine determines if the access is satisfied or it can be deleted, and decides to propagate the needed information to the successor and child accesses. These atomic state machines are finite state machines on which the state diagram has no cycles and can only be modified through atomic operations. Inside the runtime, they are represented as bit fields, and the only way to change a bit in an atomic state machine is to receive a message or a communication from another access. After the atomic state machine has changed its state, it can generate new messages that will go towards other accesses. On the right, we have a very simplified example of what an atomic state machine could look of an in access. We start with the whole bit field as 0, so the atomic state machine is on its initial state, and we receive the first message from the predecessor that says that this access can be executed with this to read the memory location, right? So we obtain this message and we set the corresponding bit to receiving this message to 1, right? And we decide that it is time to execute the task. So the atomic state machine sends the execute task order, and that task is executed. When this task finishes, we receive the task finish message, and we set the corresponding bit to 1. And in this case, for example, we decide to do nothing because there is no action to do. We cannot delete this access or send anything yet. However, we received a message later on that a successor access has been registered. So now we have another access that depends on this one, and we have to propagate the information. So we set to 1 the bit, and we decide that we send a message to the next, to the next access. And later on, we will receive an acknowledgement to that message. And then we set the bit, and we see that this is the last bit to be set. And as we have no other bits to set, we know that we will not receive any more messages on the access lifetime. So we decide that this access is safe to delete. All the accesses in the system form a network of atomic state machines that send messages to each other. When a message is delivered, more can be generated, and this process continues. This delivery, so the fact of delivering a message and setting the bits, is a wait-free operation. And the number of messages that are generated on a specific chain of accesses is well bounded. We also use an auxiliary queue to store and deliver messages that we call mailbox. So what happens is that we look at this mailbox. If there are messages, we pop one, we deliver, and if new messages are generated, we store that back into the mailbox. And we repeat this process until this mailbox is empty. Moving on to task scheduling, the scheduler is the one that orchestrates the execution of ready tasks on worker threads, which may be, for example, one per CPU. Multiple threads can add or remove tasks at the same time and needing synchronization. Most modern task-based runtimes use work stealing for these schedulers, where there are multiple task queues, often one per thread, and when an idle thread needs work, it first looks on its local queue, and if that queue is empty, it tries to steal work from other tasks threads. However, on the common case in Openmp, in which a single thread creates all of the tasks while other threads are consuming them, work stealing behaves like a global lock, as all threads try to steal from the same place. In this regard, a global lock is the most straightforward approach to synchronize the scheduler. However, it has some obvious drawbacks. It might work well with big tasks where threads are rarely on the scheduler asking for work, but on small granularities, it causes a lot of contention for both the creator and consumer threads. And we present in this paper two concepts to implement a scalable scheduler, parting from a simple global lock concept. First is a lock-free mechanism to insert tasks into the scheduler without grabbing the lock. And second is a delegation-based mechanism to perform the actual scheduling. First, on task insertion, instead of grabbing the lock to insert tasks to the ready queue, we use single producer, single consumer queues. We have multiple queues from one per NUMA node to one per thread if we need it. And creator threads use the producer side with a local lock that synchronizes only producers and insert tasks onto those single producer, single consumer queues. The consumer side is protected by the scheduler lock. And the thread that enters to request work to the scheduler will first empty the queues into the ready queue and then grab a task. The main thing is that if there is a consumer and a producer at the same time, this queue is wait free. So we can have both a consumer and a producer at the same time. We also need another piece for our scalable scheduler, which is a lock that minimizes the time it takes for an idle thread to obtain a task. Starting from the basic locking primitive, which is the spin lock, we see that it is an unfair lock. So it is possible that one thread competing for this lock is starved indefinitely. It also causes a lot of catch traffic. To solve the fairness problem, we can have a ticket lock, for example, where we have an atomic counter where that each waiting thread will increment to obtain a ticket. So it will grab a ticket from the next ticket counter. And another that determines what thread can enter the lock. So the now serving counter, let's say. Here, when the thread inside of the lock that is currently inside of the lock leaves, it will increment this now serving counter. And then the waiting threads, in this instance, thread 8 that has the next ticket, which is 13, sees that their ticket number is in the counter, it will enter the lock. So we provide some order between the threads that are waiting. To resolve the problem of causing too much catch traffic, we can use a partition ticket lock, which is an evolution, also known as an array-based queuing lock in literature, which has an array of private catch line size regions, where each waiting thread spins on this private region instead of spinning looking at this shared variable. This minimizes the catch traffic. In this example, when the lock owner that has ticket 12 performs the unlock operation, aside from incrementing this counter, it will notify that on thread 8, the thread 8's private region. It knows that this is the next private region to do because it's the number of the ticket modulo the number of private regions. Now that we have an efficient lock, but the better thing instead of locking will be to not having to grab the lock at all. So here enters delegation, which is a technique that aims to minimize this lock overhead. And with delegation, waiters that want to do some mutual exclusive operation can delegate the work to the thread that is currently the owner of the lock. And this thread performs the operation on their behalf and returns the result. If this communication mechanism is faster than entering and leaving the mutual exclusion region, which it usually is, it provides performance benefits. We use this technique in our final version of the scheduler lock. The delegation ticket lock is our final lock, which expands on the partitioner ticket lock with delegation. Note on this example, we have thread 1 that is currently inside of the lock, and thread 8 is the only waiter right now and is waiting outside. We still have the same wait array, right? This wait queue that we saw on the partitioner ticket lock, but we also have the request and result arrays. When thread 8 grabs a ticket, it also places a request on its private region, specifying the thread ID plus the ticket number. With the thread ID, the thread inside the lock can, for example, see this request and grab a task from the scheduler on behalf of thread 8 and place it on the result array on the highlighted position. When thread 8 is finally unlocked by changing the number here on the wait queue to 13, if it sees that this result has been set and is no longer this -1, for example, it will not enter the exclusive, mutual exclusive region and just grab the result and use that. Otherwise, if the result is still -1, it means that the thread inside the lock did not get to see the request, and thread 8 has to enter itself inside of the lock and grab the lock. Combining both concepts, we see a possible timeline of task creation and scheduling here on the right. Here, thread 0 is adding tasks to the queues without locking, right? So thread 0 can focus only on task creation because the add operation is non-locking for him. On the other hand, thread 1 is the first to arrive to the scheduler to request some work, and it will grab the ownership of the lock here on green. Thread 2, 3, and 4 have arrived simultaneously to thread 1 and have placed their requests on the request queue. Then thread 1 signs so grabs tasks in behalf of thread 2, 3, and 4 and communicates the result to those threads, which can just grab the task and start executing it right away. When thread 1 has finished all the requests, it can grab a task for itself and execute it on this thread. We mentioned that the third component of the runtime is the memory allocator, which is a common source of contention. In our analysis, it became clear that to achieve state-of-the-art performance, we needed fast and scalable memory allocation in nanosticks. We selected one of the already existing state-of-the-art solutions, which is called gemalloc, and we will show that the effect that allocation has on runtime performance on the evaluation section. To find all the problem areas we optimized in this paper, we extracted the information using a lightweight instrumentation framework that uses the common trace format. We implemented this instrumentation using per-core circular buffer event buffers that allowed us to have almost zero overhead tracing, which is essential to observe certain scenarios. We can also collect kernel events and hardware counters, which allow us to explore how operating system noise affects our HPC applications. For our evaluation, we used 8 benchmarks, a mix of memory and compute both applications, and we executed them in 3 architectures: an Intel Xeon 48 core processor, an Amazon Graviton 2 ARM 64 core platform, and an AMD Rome 128 core and 256 thread platform. We had implementations of its benchmark in OMPSS2 and Openmp, and we used the best available BLAS libraries for each platform. We also use DCC 9.2 and LLVM 10 as the Openmp runtimes, together with a vendor implementation if there was one. So that was mainly Intel Openmp and the AMD AOCC implementation. In the evaluation, we measure efficiency versus granularity. We define the efficiency as the percent of the peak performance of a benchmark on a given platform, which allows us to have a relative measure of performance at each granularity. We can also understand this as normalized performance, for example. On the other hand, granularity is the size of the tasks measured in average instructions executed. Maintaining better performance on smaller granularities means that a runtime can scale out with a fixed problem size better than another one. Here we see the comparison of the version of Nano 6 that has all of our improvements in blue here, and then the three versions, each one without one of the components. The brown version does not use the malloc, the orange version does not use the old, uses the old block-based dependency system of Nano 6, and the green version uses a simple global lock in the scheduler. As we see, depending on the benchmark in the machine, some optimizations affect more than others, but overall it is obvious that each optimization contributes significantly to performance on small granularities. So on most benchmarks, the scheduler is the most important one. For example, here on the mini AMR, this scheduler having a global lock means that on the smaller granularities here on the left, the performance is much smaller. Thus, this application would scale out worse. For example, there are other cases, for example, the heat on the ARM machine where the dependencies were the most important factor, or the mini AMR on the Intel Xeon, for example, where the memory allocation plays a huge role as well. So it varies depending on the machine and the benchmark. These are the same results in AMD ROM, whether it is interesting to see that with even more threads, some optimizations acquire even more importance. Here we present the comparison of OMPSS2 with state-of-the-art Openmp runtimes to give some context to the actual performance figures. It is worth mentioning that both the Intel and LLVM runtimes are similar in implementation between them, and both are based on work stealing scheduling. For all benchmarks and machines, Nano 6 delivered the better performance on the small granularities on the left of the plots, enabling applications to scale out more. Similar results were obtained in the case of the AMD ROM machine, with different behavior in the presence of SMT on the machine that had the most cores of all. Finally, we also wanted to give a glimpse of how we analyze in much more detail runtime behavior with different optimizations. This example trace shows an application with a delegation scheduler on the top versus a simple log scheduler on the bottom. As can be seen on the top, there is much less time spent by the threads waiting on the log, which is shown in this green color. Right, so on the top, there is a lot more of task execution and a lot less of log contention. When we zoom in here on the right, we can see how the bottom thread on the delegation case is assigning tasks to all the other threads one by one because they are delegating the operation. On the bottom case, for example, each task has to enter itself into the scheduler to grab a task that may not exist yet. More importantly, on the top trace, we see that the thread that is creating the tasks, which is this one here, is completely uncontended and unaffected by the fact that there are other tasks, threads going into the scheduler to grab some tasks. However, on the bottom trace, the thread that is creating the task has to wait until all other threads have entered and left the scheduler, has to compete for the log to go in and placed a new task. As conclusions of our work, we have introduced several novelties. We described a novel wait-free approach to dependency management. We proposed a scalable scheduler that can outperform work stealing-based runtimes. We identified critical contention points thanks to our fine-grained instrumentation. And our evaluation assesses how our improvements combine to outperform state-of-the-art runtimes. Thanks for watching this talk. Please refer to the paper for more details, such as proofs of the wait freedom and detailed descriptions of the scheduler mechanism.